Hi everyone, welcome to week 2. This is chemistry tutoring of 222, the general chemistry series. This week we will be going over enthalpy and kinetic molecular theory. So I'm going to jump right into it. We're going to be working on chapter 5 and chapter 9. Hopefully you can see my screen okay. But yeah, let's get started on these problems. So in chapter 5, we are going to be working on the problems listed above here, and chapter 9, these questions. So chapter 9, we're going to be working on some lower level problems, but chapter 5, we're going to be going into the root of the problems. Okay, so for the first one, we have question 40, and it asks, using the data in the Check Your Learning section of example 5.5, calculate delta enthalpy in kilojoules per mole of AgNO3 aqueous for the reaction described by the following reaction. So we have sodium and then the AgNO3, and it makes a solid form and an aqueous form of those two compounds. Okay, so I checked the data in your Check Your Learning section, and what it gave us are these two data points right here that I already jotted down. So we have 100 milliliters of the 0.200 molarity of the AgNO3 aqueous solution, and we have, for the reaction of this, 1.34 times 10 to the third power joules, or 1.34 kilojoules for the entire reaction. So using those two things, we can find the amount of energy per mole of this compound that is created from this reaction. So what we first need to know is, well, we're finding kilojoules per mole, so we need to know how many moles of this we have. So we can find that from this data point right here, the 100 milliliters of this molarity, the 0.2 molarity. So we can do that. So using that data, we can start with the 100 milliliters of AgNO3, and this is of the aqueous solution, and then multiplied to cancel out the milliliters. Since molarity is in moles per liter, we need to cancel out with liters, not milliliters. So cancel that out, and then we can go from liters to moles. So in 1 liter, there's 0.200 moles of the AgNO3 solution. So multiplying all of that out will give us how many moles we have of this. And so we'll have 0.02 moles of the AgNO3 aqueous. And it's important to note to write the aqueous right there because we have a reaction going on. We have an aqueous version, and then we have, I believe, the salt, it said. So the salt, and then AgNO3 aqueous, and then Ag chloride, and then the NaNO3. So those are the 4 things that we're working with, and like I said before, we're trying to find the AgNO3 aqueous. So now that we have the moles of how much we have of the AgNO3 aqueous, now we can simply divide it by how much is going to happen in the reaction. And so when we look at the equation here, we can see how there's 1 mole of every single thing. So there's a 1-to-1 ratio. So for every 1 mole of the NO3 aqueous, there's going to be 1 reaction of energy. The reaction that was given right here, the 1.34 kilojoules. So it's just a 1-to-1 thing. So for every 1 mole of AgNO3, since that's what we have here in this equation, we have 1 mole of AgNO3. There's going to be 1.34, that's a 1 right there, 1.34 times 10 to the third power of kilojoules, of joules. And so that's going to give us just 1.34 again times 10 to the third power of joules. And so since we have the energy here, and this is of the AgNO3, so since we have the energy and the amount of moles of this, we can just divide the two, and then we will get the delta enthalpy for this. So let's write that down. So the delta H is going to be 1.34 times 10 to the third power of joules divided by how many moles we have, and we have 0.02 moles AgNO3 aqueous, and that's going to equal 67,000 joules per mole. Or, since it was asking in kilojoules, just dividing by 1,000 will give us 67 kilojoules per mole. So that is the answer for this problem. It looks more complicated than it is, but it's not as complicated to calculate, which is nice. So that is the first problem done. Let's move on to the second one. This is problem 46. And the question states, how much heat is produced by combustion of 125 grams of methanol under standard state conditions? So, we first need to recognize, how do we write an equation for combustion? So we have methanol, and methanol has the compound of CH4O. And in standard state conditions, this is a liquid. And so that's what that means when it's a standard state conditions. What is the standard state of it at like room temperature? And it's a liquid. So that is the compound that we're working with for methanol. That is what methanol is. And for combustion, it's always going to be that thing plus oxygen gas creates CO2 and water as the byproducts. So let's write that down. So for this reaction, oxygen gas goes to CO2 gas plus H2O water. So that is our reaction. So you can see maybe already that the hydrogens, carbons, and oxygens aren't balanced on both sides, so we need to do that still. So we have carbon, hydrogen, and oxide. I'm just going to put that, or oxygen, I'm going to put that on the left and the right so we can count it up and double check. So for right now, on the left side, we have 1 carbon, 4 hydrogen, and 3 oxygen. On the right, we have 1 carbon, and I believe 2 oxygen, and 2 hydrogen, and 3 oxygen. So we have too many hydrogens on the left, and that seems to be the only thing, but since the hydrogen is only on the methanol side right now, it'll be adding towards oxygen and carbon content as well, but that's okay. So let's add a 2 to that compound there, the methanol, and so that'll make everything different. So now we have 2 carbon, and now we have 8 hydrogen, and we have 4 oxygen. And so now on the right, we're going to have to add a 2 next to CO2 so that the carbon is equal. So now on the right side, we have 2 carbon, we have 5 oxygen, and we have 2 hydrogen still. But now the hydrogen is not balanced, so now we need to put a 2 in front of the water. So now that'll make everything different. So now we have 4 here, and it looks like we're going to have to add even more hydrogen. So since, before I continue with that calculation, because there's hydrogen on the left and it's 8, we need 8 on the right. So I'm going to put a 4 in front of the hydrogen or the water here so that there's 8 hydrogen. So we won't need to mess with that anymore. So that'll have 4 times the oxygen here, so that's 4 plus the 4, so that'll be 8 and 8. Okay, and so it looks like it's almost checked out. So because there is 8 oxygen on the right, we're going to need to add 4 more of the oxygen on the left, and the only thing that has only oxygen in the term is the oxygen gas. So we're going to put a 2, or let's see, 2 more, so we need a 3 in front of that. And so that'll do 3 times 2 is 6, 6 plus 2 is 8. So we have 8 oxygen on the left, 8 oxygen on the right. So now everything is balanced. And so now we have a fully balanced reaction here that we can work with. So let's get started with answering this problem. So it says how much heat is produced. So this is also known as the Joule amount. And since we have an amount of 125 grams of this, that's what we are going to start with. So we have 125 grams of CH. And since we're in grams, we want to go to moles. And then in the final end, we want to go, because we'll be using the standard state condition value of moles and the energy that every mole of the methanol, how much energy is produced. This is just a standard value. It's a table in the textbook, so I'm going to be using that as the last step. And since that's in kilojoules per mole, we will need to find just the end result of the energy. So we need to cancel that with moles. So working backwards, we have energy per mole. We want to end up with energy. So cancel out moles. How do we do that? Molar mass. Because we start with grams, cancel out grams, get to moles, cancel out moles, we get to energy. So let me write that all down so that as written that makes more sense. So we have 125 grams, and the molar mass of this is 32.04 grams per 1 mole of CH4O. And so for every 1 mole of CH4O, we have negative 239.2 kilojoules produced of the CH4O. So that's what that looks like. And so calculating that all out, I already did this earlier. So the answer is negative 933 kilojoules of energy. And so that is the answer to this problem. Since it was an exothermic reaction, it makes sense that this might be as well, because it's releasing heat to be able to break this down, or not break it down, but to transform it into CO2 and water. So that is the answer to 46. So let's move on to the next problem. Our problem is 49. The question is, when 2.50 grams of methane burns in oxygen, 125 kilojoules of heat is produced. What is the enthalpy of combustion per mole of methane under these conditions? So it's going to be very similar. We're going to be practically doing the same exact thing we did last time. We first need to write the equation for this. And so let's write this down. So we have methane. So methane looks like this, CH4, and it is a gas. And with a combustion reaction, it's going to react with oxygen gas. So let's write that down. And then it goes to CO2 and also water. And so to balance this, we have too many hydrogens on the left, so we need to put a 2 in front of this water. So that is balanced. So now we have 4 hydrogens on all sides, and we have 4 oxygen on the right, but we only have 2 on the left. So all we need to do is put a 2 in front of the oxygen gas on the left, and that is all balanced. So let's move on to getting started. So we have a mass of methane, so we want to start with that mass. So we have 2.50 grams of CH4. And so we need to go to the molar mass again because we want to get this into moles instead of grams. So the molar mass of CH4 methane is 16.04 grams per 1 mole of CH4. And so that is going to produce 0.1558635 moles of CH4. So that is how many moles we're working with, and because it produces 125 kilojoules of heat when this is produced, all we need to do is divide it, because the question was, what is the enthalpy of combustion per mole? So it's just energy per mole, same thing as the first problem I believe we worked on. So we have the mole amount, and so we have 125 kilojoules to start with, divided by how many moles we have. So it's just the same one as we just wrote. So that will give us an answer of 801.99 continued. But since we have 3 significant figures to work with here, it's going to be 802 kilojoules per mole. So that's the answer to this problem. It's always key to note, like when they give a volume or a mass of something, usually that's what we first start out with, and then we kind of work our way through some analysis to get to whatever our end goal is, right? And we want a kilojoules per mole, so we need moles, we have kilojoules, divide them by each other. So that one's pretty lower on the calculation part. Let's move on to 55. Okay, so 55 says, does the standard enthalpy of formation of water in the gas form differ from the standard enthalpy, or the enthalpy change for the reaction hydrogen gas plus oxygen gas equals hydrogen gas? So this one is different. So the answer is yes. The standard enthalpy for hydrogen gas, and it's key to note it said for 1 mole of hydrogen gas is different from this reaction because we have 2 hydrogen gases related. We have 2 moles of it. So it's going to be 2 times the standard enthalpy value of it, because the standard enthalpy values that you find in tables or on the internet or what have you, that is going to be per 1 mole of that compound, that whatever gas, liquid you're trying to find. So since this is making 2 of it, it's multiplying by 2, because you've twice the amount, it's going to produce or take in twice the amount of energy. So yes, it is different. For 1 mole versus 2 mole of hydrogen gas created. In joules. I'll add that. There we go. That is the answer. So let's move on to 59. 59 is a long problem. It takes a little bit of working through to really understand these problems because they're a bit complicated. Even though the principle of it is simple, it can get kind of messy. So the problem is the following sequence of reactions occurs in this commercial production of aqueous nitric acid. So we have 3 different reactions here, and they have 3 different enthalpy values for each of these reactions. So what we want to do is we want to switch these around. We want to multiply them by different coefficients to get to the final equation and the final amount of energy that it takes for the entire thing. Because each one of these reactions are not necessarily cohesive. You just add them all up because you're not going to have the simplified down version of what is actually going into making the nitric acid. Because this actually, this is the reaction that's formed, but it might be switched around that it actually is going to be used in the reaction to make the nitric acid. So that's why we have to switch things around and multiply things by different coefficients. So let's get started with that. So let's look at each of these individual equations to try to see which ones are repeated, and that we need to swap the equation around. So multiply by a negative value for the energy. So instead of creating energy, maybe it's taking in energy because we swapped it. So let's write down, or maybe just highlight which ones are repeats and that we might need to switch. So looking at all of these, we have NH3, we have oxygen gas, we have NO, we have water, another oxygen gas, an NO2, another NO, another NO2, another water, HNO3, which is the nitric acid, and then another NO. So the things that we need to pay attention to here is specifically the NO first. That's the one that I'm going to start out with because that is the repeat, and that is not needed in the final reaction. So let's see. Okay, so we have the NO here and the NO here. So I'm going to be using the first 2 reactions right here to manipulate, to cross out, or kind of simplify down to get rid of the NO. So let's write down those equations again. I'm just going to highlight and select it save on time. Copy and paste. And these are the enthalpies as well. Okay. And so we see that whenever we are able to cross something out, they have to be on opposite sides of the reaction, so opposite sides of the arrow. The NO's on this side, NO's on this side, so we don't need to flip anything right now. So all we have to really pay attention to is the coefficients. And so this is a more simple one to do because it's just a 2 and a 4 ratio, so we just need to multiply the 2, so this entire reaction by 2. So I'm just going to put a 2 times right there, and then also times a 2 right there to keep track of everything. And so 2 times that is going to give us negative 226 kilojoules. And so when we multiply it and then add these two, so we're going to add all these two reactions together, what that will be is we'll keep the top one. So I'm going to just write down this first because nothing's being canceled out here, being aware that these oxygens are going to be added. So we're keeping the 4NH3 gas, and then because we have 5 of the oxygen gas on the top and now 2 oxygen gas on the bottom, now we have 7 total. And besides that, we have the 4NO that we just multiplied that we want to get rid of, and we'll have the 4NO on the right, so we don't need to cancel those out since this will be gotten rid of. So let's get rid of that. And then that will go to the 6H2O that we still have and we didn't do anything to, and then we'll have 4NO2. So that is the final combination of the top two equations, or not the final, but in progress version. So now to find the total enthalpy, we need to add all of the two separate ones together since we combine those two. So the negative 907 and then the negative 226. And so the enthalpy created will be negative 1,133 kilojoules. So that is the enthalpy created from those two reactions. And so now I'm going to add in or write down the third reaction below. And we have 3NO2, just rewriting it, gas plus H2O, liquid, makes 2HNO3, that's our nitric acid, aqueous, plus NO gas. Okay, so let's look at this here. I'm putting these parentheses because I have a feeling we're going to need to multiply these equations out. So the thing that is repeating, like we stated earlier when we were going through everything, is the NO2 right here. So this NO2 is being repeated. So we'll need that to go away. And the reason why I'm getting rid of the NO2 because of the water is because this is an acid, so we'll need water for that to be created. So when we're going back to the things that we're repeating, we need the gas and we need the water. So the O2 and the water, that's why we're not canceling those things out. We're only canceling out the, let's get this red, the NO and the NO2. So those are the things that we don't need because we're getting the nitrogen from the NH3 that doesn't have any duplicates anyway. So it's kind of easy to tell we're not going to get rid of it because we can't. So that's going to be staying, the NH3. And so we won't need the nitrogen, the NO or the NO2 because of that. And then we will need the oxygen gas in the water, like I said before. So that's just to keep that in mind. That's why I got rid of those things, because if you simplify and cancel other things out, you're not going to get the right answer because that is not the final formation equation for the nitric acid. So just keep that in mind as well. So since we're getting rid of the NO2, we can see that the coefficient is a 4 and the coefficient is a 3 on these two gases. But what is good, and we don't have to multiply anything by negative because they're on the opposite side of the arrow, so we don't need to swap anything around to cancel it out. So a common factor of 4 and 3 is 12. That's the earliest value on. So all we have to do is multiply by each other's value to each of these equations. So we're going to multiply the 4 on the bottom and 3 in the top, since they have that value vice versa for their coefficients. And so because I'm multiplying, you also need to multiply by the energies. So times 3. And then this one, enthalpy value that they gave is negative 139 kilojoules. So I'm just going to write that down. Negative 139 or kilojoules. And then times by 4. And so adding up all that together, actually before we add it, let's have this all added. Plus and so let's see what everything goes to here. I'm going to write above each one of these what the number will be, so we don't have to do it again. So 3 times the 4 NH3 on the top will give us 12. Let's put it smaller. Will give us 12. So we'll have 12 of that. 3 times 7 will give us 21. And the 3 times 6 is 18. 3 times 12 is, or 3 times 4 is 12. And 4 times 3 is 12. Actually, let me put that right there. And then 4 times 1 is 4. 4 times 2 is 8. And 4 times 1 is 4. So those are all the coefficients for everything. So let's just write everything down. It sometimes makes it easier if you write it out like that. So now we'll have 12 NH3 gas plus 21 O2 of the oxygen. And it's important to note also that the NO2s are going to cancel out. So I'm just going to write that, cross those out. And so we still have water on the left here. But before we do that, to make it easier for ourselves in the future, we have a 4 on the left and an 18 on the right. So these 4s are going to go away, and we're going to take 4 from the right to balance them, because there's duplicates and we don't need any duplicates. So we're not going to put any water on the left, but now we will. So on the right, we're going to have water. So we have 14 H2O, so I'll write that, 14 H2O liquid, and then we have the 8 plus 8 HNO3 of the aqueous, and then we're going to have 4 NO of the gas. So that is the final reaction here. Everything multiplied out. We can actually, now looking at the coefficients, sometimes you can balance it to make your life a little bit easier for finding out how much energy is produced per 1 mole of whatever you're finding. Here we're going to find, how much of the nitric acid. So we have 8 moles here, but we can't simplify anything down because we have a 12, a 21, 14, 8, and 4. So the 21 prohibits us from dividing by 2 because we want whole numbers in the coefficients. So we can leave it alone. So let's add up the energies on the right. So the negative 1,133 times the 3, and then adding that with the negative 139 times 4, out of everything added up, it'll be negative 3,955 kilojoules. And so from that is the entire reaction here. But we need to, or that's the entire reaction for the nitric acid, but we're creating 8 moles instead of oh sorry, that this amount of energy is for 8 moles, so we will need to find it for 1 mole. So we need to divide that total energy by 8. And so when we divide it by 8, so let's just scoot this down just a wee bit. So when we have negative 3,955 kilojoules divided by 8 moles, that will give us a total amount of negative 494 kilojoules per 1 mole of nitric acid produced, but that is implied here. So that is our final answer. So like I said before, these problems can get pretty complicated. It's important to make it as easy as you can and clean up some things before you proceed, because let's just say if I didn't add these 12s here, I know it's a little thing, but if I didn't like kind of add this up before doing it down here, I might have made a mistake, and it's easier to see like, oh, I put a 22 instead of a 21. Why did I do that? Let's go back here and kind of see what my process was. So it's good to keep note and like bookkeep kind of how you're multiplying these coefficients and simplifying them down. Sorry, this sun is right in my eye. But yeah, so that's the final answer for this reaction. Let's move on to 68. So 68 asks, using the data, calculate the standard enthalpy change for each of these reactions. I love this problem because these are much more simple in my mind than trying to find the total energy per mole of whatever for 3 different reactions, because like I was saying in the last problem, it's a little bit complicated. These are quite simple. You just look up the values, you multiply it by how much ever you have, and then you kind of subtract you do subtract the products from the reactants. And that's really it. There's no finagling or anything like that. So the first one we have is nitrogen and oxygen gas equals NO gas. So because the NO or the N2, so I'm just gonna write here HF, this is enthalpy of formation of N2 gas, O2 gas, and NO gas. So because, like I was saying, the oxygen and the nitrogen gas, excuse me, because they're in standard state, they have zero amount of energy, because you don't need to put any energy in to change them into anything, so they're going to have a 0 value. And that is all for standard state gases, liquids, solids, whatever. But the NO gas is, the NO gas is not. So just looking that up in the table in the textbook, that's what you're supposed to do, gives us a value of 90.25 kilojoules per mole. And because we have 2 moles in this equation, we're going to multiply it by 2, and that gives us 180.50 kilojoules for this total reaction. Because it's making the nitrogen, the NO gas, our standard enthalpy here is in the form of the formation of this gas, and so we don't need to multiply it by a negative or anything like that, because it's already going into the products, and that is our final answer, the 180.50 kilojoules. So let's move on to the next problem. This is problem B, 68B, and we have silicon and chlorine gas makes a SiCl4 gas. So let's write out what we just did similarly. All the delta HFs of Si, solid, chlorine gas, and Si, chlorine 4 gas. Okay, so similarly to the last one, the silicon in the solid form and the chlorine gas in the gas form, they're both in their standard state conditions, so they both have 0 enthalpy values. So we don't need to do anything there again. But the silicon and the chlorine compound here, that is not going to be 0 because it's not in standard state. So we have from the textbook negative 662.75 kilojoules per 1 mole of reaction of the formation of this. And because from the formula here, or from the equation, reaction, we have 1 mole produced for every 1 reaction. So we're going to multiply this by 1 mole, which is just the same number, which is negative 662.75 kilojoules produced. And again, because this is going to be the product, and we're using the enthalpy formation, so product value, we don't need to multiply it by a negative because it's already in the correct order of things. So that is going to be our answer. So let's move on to the next one, which is C. So we have an iron oxide, we have hydrogen gas making iron and water. So just as we did as the last time, we have 4 different things. So let's write down the delta HFs. Delta HF, delta HF. And we have Fe2O3 solid. And make sure you write down the state of it. So if it's a solid, liquid, or gas. Because, if we're having water as a gas or a liquid, that's going to change the formation value of it. So hydrogen gas, and then we have iron, and we have water. Okay, so because the hydrogen and the iron are in standard state conditions, just as we talked about, that is going to be a 0 value. But the iron oxide and the water formation are both they're both non-zero values for the enthalpy formation. So let's write down those values. So for the iron oxide, we have negative 824.2 kilojoules per mole. And from this equation, we only have 1 mole of the iron oxide, so we don't need to multiply it by any other value than 1, so multiply it by 1. It's just going to give us the same value back, negative 824.2 kilojoules. And for the water formation, we have a value of negative 285.83 kilojoules per mole. And looking at this reaction, we have 3 created. So we're going to multiply it by 3 moles instead of 1. And that is going to be give us a value of negative 857.49 kilojoules. So instead of the last ones, how we could just write down the non-zero value of the enthalpy we got, this one actually we need to keep track of the products and reactants more thoroughly. So the water is the product, and the iron oxide here is the reactant. And so when you're finding the total enthalpy values, you're subtracting the reactants from the products. So we will have the value of negative 857.49 of the water minus the negative 824.2. So that is going to be a plus because of the 2 negatives. And so we will get a final, I'll write that down here, a final enthalpy value of negative 33.29 kilojoules. So that is the answer here. So let's move on to the last one of these. So this is the lithium hydroxide plus CO2. And it makes Li2, CO3, and some water gas. So, like I said last time, keep track of if it's liquid or gas. Sometimes we can switch these up on accident. Because it's water, we sometimes assume that it's going to be liquid when we see water. So just as we did, let's write the delta HFs for all of these. So we have the lithium hydroxide, solid, we have the CO2 gas, we have Li2CO3. solid. And we have the H2O gas. So of these, none of these are, I believe, except for, no, yep, all of them, I've already checked, all of these are not in their standard state condition, so they all are going to have a non-zero value. So let's write down all of those. So for the lithium hydroxide, we have negative 487.5 kilojoules per mole. For the CO2 gas, we have negative 393.51 kilojoules per mole. And for the lithium carbonate here, we have the negative 1216.04 kilojoules per mole. And finally, hydrogen gas, we have negative 241.82 kilojoules per mole. And so now that we have all of the enthalpy formation values, all we have to do is go to the equation that it gave us and then look at the coefficients of each of these members and then multiply it by how many ever moles that we have, just as we did in the last 4 problems, I think. So for the first one, the lithium hydroxide, we have 2 of them, so that's multiplying by 2 moles. The second one, the CO2, we only have 1. So multiply it by 1 mole. And then the lithium carbonate one, we have 1 mole. And then for the hydrogen gas, we also have 1. So 1 mole. So all of these will be equal to negative 974 kilojoules, negative 393.51 kilojoules, negative 121604, and negative 241.82 kilojoules. So those are all the answers, or not answers, not final answer. Those are all of the formation values of each of these terms. So now we need to look at which ones are products, which ones are reactants. So for the products, we have the LiCO3, and then we have the water gas. So we're going to add up the products, so those 2 things right here, and then subtract them by the reactants. So delta H total is going to be the negative 241.82 minus, or adding the negative minus, same thing, 121604, and then minusing the products, or the reactants. So let's add those up. So negative 974 minus 393.51. And so adding up all of those will give us a value of negative 90.31 kilojoules. So that is the final enthalpy value that is needed to form this reaction. So we are done with all of the parts of 68. So let's move on. I believe this is chapter 9 now. So moving on from enthalpy values, let's talk about some gas stuff. And PivNert, I like to say, because that is the reaction that we're going to be working with, or the equation. So we're on question 6, and it asks, or says, a typical barometric pressure in Kansas City is 740 torr. What is this pressure in atmospheres, in millimeters of mercury, and in kilopascals? Okay, so these just have to do with conversion values, of knowing from how much of one pressure is equal to another pressure and just doing some unit conversions. So let's do that right now. So we're working with 740 torr, so that's what we're working to begin with. So it asks this pressure in atmospheres, highlight to keep track of everything, millimeters of mercury, and in kilopascals. So for torr to pascal, it's I think the most complicated conversion of them all of the pressures. It's for every 760 torr, we're going to have 101,325 pascals. And since we need kilopascals, we need to divide it by 1,000. So for every 1,000 pascals, we have 1 kilopascal. And so multiplying that out will give us a value of 98.6 kilopascal. So that is the same pressure in kilopascals. Let's convert it into millimeters of mercury. So we have 740 torr. And actually for torr to millimeters of mercury, it's a 1-to-1 ratio, so we'll also have 740 torr, or millimeters of Hg. And it seems I forgot to already calculate how much torr is to atmospheres, so I'm going to look that up on my phone real quickly. Torr to atmosphere conversion, just to know the value. And so the conversion of that, so for 1 torr, let's move everything down. So for every 1 torr, we have 0.0013 atmosphere. I like to write ATM, and you'll see a lot of that written down as that abbreviated. So multiplying that out, we will get 740 times 0.0013. So we'll get 0.962 ATM. So that is the answer for atmospheres, millimeters of mercury, and kilopascals. Let's box everything. Awesome. So let's move on to question 20. So this one asks, one way to state Boyles Law is all other things being equal, the pressure of a gas is inversely proportional to its volume. So it has 2 parts. It also asks, what is the meaning of the term inversely proportional, and what are the other things that must be equal? So as I stated before, we're going to be using the equation PIV-NERT because that is Boyles Law. And so PIV-NERT is exactly what I mean. PV equals nRT. And so each of these things stand for pressure, volume, number of moles, the constant R, and temperature in Kelvin. So because this is talking about Boyles Law, PIV-NERT, and it's talking about, the pressure and also the volume, these are the 2 things that it's talking about, the pressure and the volume. And it says if everything else is constant, so that's the part B in this question that it's asking. That is talking about the nRT, because if nRT is always remaining the same, we're going to be getting the same change from pressure and volume, because the nRT is going to always be there, so that's not the thing changing. So the answer for B, at least, is the number of moles, the constant value, so that's just constant value, R, and also the temperature in Kelvin. So that is what all of these things, or those are the things that are staying equal. And so when it asks the term of, what does inversely proportional mean, it practically just means because of these things are on the same side, to get them isolated to each other, you have to divide by them. So for pressure and volume, you have to divide each side. So let's just say this was the same, right? Because it is the same in this problem. You would divide both sides by V, for example, and you would get pressure equals 1 over V, or V equals 1 over P. It doesn't make a difference in this problem because inversely proportional just means when one goes up, the other one goes down. And it's going to have an inverse relationship because of the inversely proportional equation from PIV-NERT, Boyles Law. So let's move on to the next one, which is very similar. So Boyles Law, also we can talk about the volume and also the number of molecules in the gas. So it's, if all other things being equal, the number of molecules in a gas is directly proportional to the volume of gas. What does directly proportional mean, and what are the terms that are equal? So just as last one, like I said, this is the equation that we're working with. And when we're keeping the number of molecules, N, and the volume, V, the different, so those are the two things that are varying, and everything else is equal, everything else that is equal is the pressure, the constant, and the temperature. So the pressure, the constant R, and the temp. So those are the things that are equal. And so the V and N, it's asking, what does directly proportional mean? It just really means that to solve for the volume and the number of molecules, when one goes up, the other one goes up. So that's basically what directly proportional means. So this increases, then this increases. This goes down, then this goes down. So that is simply what those mean. So let's move on to the final one of today. It asks, determine the volume of 1 mole of determine the volume of 1 mole of methane gas at 150 Kelvin and 1 atmosphere pressure from the figure. So I pulled up the figure that I was talking about. And so this graph on the right is 1 mole of methane gas. That's what it stated, like the description above it. And it is at 1 atmosphere of pressure. And so since it's asking at 150 degrees Kelvin, I will zoom in on this. So when we go to the temperature on the bottom, it's asking for the volume. Keep that in mind. This seems to be the 150 mark right here. And so the volume that it crosses at is around here. And so it's like halfway in between, it's a quarter N. So between 10 and 20, right here it's 15, right? So 10 to 15, half in there, it's going to be a value of around 12.5 liters. So that is the amount of volume that the 1 mole of the methane gas will be at that temperature. So those are all the problems that I have for everybody today. Let me know if you have any questions. I will be posting this to the YouTube on the PSU Learning Center channel. So if you want to rewatch this, go over anything, leave a question. Then if you want to rewatch it, let me know if you need the link. I'll probably post that in with the video as well. But I will see you all next week. Have a great weekend, and I hope the next week of classes go well for everybody. Bye.